This is part 2 of our notes for Monday, November 30th. We're going to look at angle bisectors now. We looked at perpendicular bisectors of a segment. Now we'll take a look at angle bisectors. What you'll find is the theorems are very, very similar. First of all, before we take a look at the theorem, need to point out something about the distance between a point to a line. When we talk about distance, we always go the shortest length. Or measure the shortest length between two things. And what it turns out to be is that the distance between any point and a line is the length of a segment that's perpendicular, or the length of a perpendicular segment from that point to the line. And we're going to use that in these theorems. Okay, so the theorem for the angle bisector, or the angle bisector theorem. It says if a point is on the bisector of an angle. Now, the point that we're talking about in this theorem is point C. Okay, it's the angle we're looking at is angle APB. And so C is somewhere in the middle of that angle, or it's in between, on interior. Let's use that word. It's on the interior of the angle. And it is actually on the bisector of the angle. And if you can see the arcs down there at angle P, we're showing you that segment, or the ray from P through C, is actually cutting the larger angle into two equal parts. Or in other words, angle APC is congruent to BPC. All right, so we have our hypothesis. Point C is on the interior, and it is on the bisector of the angle. The conclusion is that it is equidistant from the sides of the angle. So it's telling us that the conclusion that AC is congruent to BC. And when you do those measurements, we measure the shortest length in there, and that's why they're drawn as perpendiculars. If you notice, we end up making two right triangles out of them. The converse of that theorem is also true. Converse meaning that we exchange the hypothesis and conclusion. So the converse says if a point, again meaning point C, is in the interior of an angle and is equidistant from the sides of the angle. So that's using the hash marks. We know that it's equidistant. It also tells us that these are right angles. So it's lots of information in that hypothesis of the converse. So if a point is in the interior of an angle and it is equidistant from the sides of the angle, then it is on the bisector of the angle. So the conclusion this time is that the two angles APC and BPC are congruent. In other words, it splits the angle, large angle, into two equal parts. Two equal parts. The theorem and its converse are true. If you want to think way back, we could write those two together as a biconditional with an if and only if statement. That kind of takes us back a bit. All right, so let's see how we could apply these. So first one, and again, I'll see if I can keep that theorem where you can see it. First example. The picture I've drawn is very much like the picture in the angle bisector theorem. We can see that we're given angle JKL and KM, that ray KM is bisecting that angle. So it bisects angle JKL. And since M is on that bisector of the angle, then that means it is equidistant from the sides. So since JM is 12.8, LM will also be 12.8. And that is just using the angle bisector theorem. Angle bisector theorem says that JM will be exactly the same length as LM because they are equidistant. M is equidistant from the sides. Okay, so that was pretty straightforward. Let's take a look at another one. This one. given an angle ABC, that's that very large angle, it is 112 degrees. The whole angle is 112 degrees. Let me draw that in here. 112 degrees. There you go. And if we take a look at the picture, we can see the right angles. That what that is telling us is that AD is perpendicular to AB. And we can also see from the picture that AD, that length, is the same measure as CD. So AD equals CD. The segment AD is perpendicular to AB, and DC is perpendicular to BC. Let's go back and take a look at that converse again. It says if a point is on the interior, so we're looking at point D, is on the interior of an angle and it's equidistant from the sides. Well, point D is 74 from one side and a length of 74 from the other side. So it looks like we're set up to use the converse. It says then it, meaning point D, is on the bisector of the angle. So by the converse, D, or in other words, BD, let's just write that ray, is the bisector of the angle. So it bisects angle ABC. Well, if it bisects it, it cuts it into two equal pieces. And our total angle is 112. So half of that 112 degrees would be 56. So each small piece is 56, and ABD is one of those small pieces. So it is 56 degrees. That is using the converse theorem. So example 1 used the theorem, angle bisector theorem itself. Example 2 used the converse. We have one more example. Let's see if we can figure out what it's going to be using. All right, so we're going to look at the picture again. Let's see, from the picture, we can see that RU is the same measure as TU. We don't know what it is, but it's marked with hash marks. That is the distance from point U to those two segments. We can also see that UT is perpendicular to ST, that ray, and segment UR is perpendicular to SR. So by the converse theorem, that tells us that SU, that implies that SU, that ray, bisects our angle. Bisects angle RST. And we're trying to find S or TSU. That's one half of that large angle. Okay, we have enough. Since it bisects it, the 5Z plus 23 has to equal the 6Z plus 14 because those are each of the two halves of the larger angle. So if we can solve for Z, we can find the measure of one of those angles. So let's solve this. If we subtract 5Z from both sides of that equation, we get 23 equals Z plus 14. Subtract 14 from both sides of the equation, we'll have Z equals 9. And TSU is 5Z, which is 9, plus 23. That's 45 plus 23, or a total of 68 degrees. Total of 68 degrees. So again, the first First example, we used the bisector theorem. The second two examples, we didn't know, originally weren't given the information that our point was on the angle bisector, but we found out because the distances of that point from the two sides were the same, we concluded that it was on the angle bisector, and so we could use that. So we used the converse for the second two. All right, that should have you set up to try some of these on your own.